This is Lecture 2 of Physics 1110 lectures. Today we're going to be talking about measurements, significant figures, dimensional analysis, and units, just to name a few of the things. So let's talk about theories and experiments. The goals of physics are to develop theories based on experiments. Now, a physical theory is usually expressed mathematically, and it's going to describe how a given system works. And the theory is going to make predictions about how a system should work. Of course, then we do experiments to check the theory's predictions and see if it's correct, and every theory is a work in progress. So physics is a quantitative science. What does that really mean to be a quantitative science? We use these measurements as questions to nature. So we'll take a measurement and we'll use it to try to probe what is the nature of nature? What makes things work? All right, so that asks the question, what is a measurement? Well, a measurement is a comparison to a standard. So what's a standard? A standard is something like a ruler, a stopwatch, or a mass set. It's something that everyone agrees on, that this is the correct. For example, if we would be using a ruler, we would use it, take that ruler and compare it to another standard that everyone agrees on. This is exactly what an inch is, or exactly what a centimeter is, or exactly what a meter is. Or a stopwatch is a standard because it measures seconds and will tell us how much a second is, or a mass set, or different standards. So when we're making measurements, we're usually making measurements of some dimensions, some quantities. So there's some fundamental quantities and dimensions that we want to talk about. In the first part of this class, we're going to be doing mechanics. And mechanics uses three fundamental quantities: length, mass, and time. The other physical quantities that we'll talk about can be constructed from these three. For example, velocity. Well, velocity is length over time. Well, in order to communicate the result of a measurement for a given quantity, we have to define a unit. And a definition of a unit allows everyone to relate to the same fundamental amount, so that everyone can agree that this measurement is done the same way for everyone. And in 1960, an international committee agreed to the System International, or the SI unit of measurement. It's the system that's going to be used in this text. It's used in all of science. It's also called the MKS system because those are the first three letters of the units of the fundamental quantities that we measure: length, mass, and time. So let's talk about these. Length. The units of length in the SI units is a meter, denoted with the lowercase m. And a meter is currently defined in terms of the distance traveled by light in a vacuum during a given time. More specifically, 1 over 299,792,458 seconds. This also is going to establish the value of the speed of light in a vacuum. Now, this is a lot better than, say, the standard that was used in 1120 AD. 1 yard used to be defined as the length of the distance between the nose and the stretched out middle finger of the King of England. Well, that might sound absurd, but at least it was a standard. The problem with a standard like this is every time the king dies, there's a new king, that standard might change, and everyone around would have to change it. Otherwise, people would be making measurements different. It could affect commerce, it could affect lots of different things. The unit of mass is the kilogram, kg. The kilogram is currently defined as the mass of a specific cylinder kept at the International Bureau of Weights and Measures in Surveys, France. And you can see from the picture off to the side, this cylinder is kept under double vacuum, 2 bell jars, so that it doesn't evaporate, doesn't rust, nothing happens to it, but they can pull it out and weigh it against another mass and say, yes, this is exactly 1 kilogram. And the last one is time. The units of time in SI units are seconds, or lowercase s. And there's been lots of different ways that we've defined a second. We used to define second as Well, it was 1/24th of 1/60th of 1/60 of the time it takes for the Earth to revolve one time around its axis. Well, the Earth kind of wobbles, it speeds up and slows down sometimes, and that's why, for example, on New Year's sometimes we add a leap second or subtract a leap second because of this wobble of the Earth. So we needed a better way of doing it. And so currently we have cesium atoms, and we measure the oscillation of the cesium atom in this atomic clock that you see in the picture, and they count a certain number of oscillations. Millions of oscillations will happen a second. And as soon as you get to a certain number, because it's a characteristic of the cesium atom, it's the same every time, we define that as a second. It's kind of a complicated way of measuring it, but we know it's repeatable, it's the exact same every time, everyone agrees to it, so that is our official second. Now there's, of course, other systems of measurements. There's the Gaussian system, or also known as the CGS system, named for the first letters of the units it uses and its fundamental quantities. Or the one that's used in the US all the time, called US customary. It's the everyday units that you're used to hearing. One of the things in US customary is often we use weight or pounds instead of mass as that fundamental quantity. And why that might be okay on Earth, it's not something that stays the same every time. So your weight would change, say, if you were on the moon, but your mass would stay the same. We'll talk about this more when we get into forces. So, the SI unit uses meters, kilograms, and seconds. The CGS would use centimeters, grams, and seconds. And the US customary is the foot, the slug, and the second. A slug being a slug, it used to be the mass of a British musket, the British Army's musket bullets as a slug. So when we're dealing with these different units, often we'll be dealing with a lot of them, or maybe a very small amount of them. For example, we might be talking about something that's a megameter away, 10 to the 6 meters. We wouldn't want to write down 1,000,000 every time we talked about this distance. And so instead we could use this prefix, capital M, in front of the little m for meter, so megameter, to denote that. Or maybe we're talking about a very short amount of time, say the amount of time between light pulses in fiber optics and laser communication, a femtosecond. Well, instead of writing 0.000000000000001 seconds, we could just write 1 fs, femtosecond. So each prefix has a specific name, a specific abbreviation, a specific powers of 10 as shown in table 1.4 here. You should know certainly between -9 and +9 on this table of powers of prefixes for the metric system. Now the next thing I want you to watch is this powers of 10 video. I want you to watch it to get an idea of the sizes of things in the universe. It's an older video. It was created to give the executives of IBM at the time that computer chips were started to be created smaller and smaller, and they started talking about a micrometer, a nanometer, and maybe you don't have an intuitive feel for what these are. So there was the Ames brothers came up with this video to help us visualize what all these different powers of 10 are. Like I said, it's a classic video. It's a little old. Just ignore the clothing and the music and everything. Start it up, go full screen so you can really get a feel of what's going on, and just kind of enjoy this video.